Section 5.3, to identify and use properties of triangles. First, concurrent lines. Concurrent lines is when I have three or more lines that intersect at one point. In the diagram, I have line K, line M, and line N. These three lines intersect at this common point. That common point is called the point of concurrency. In other words, it is the point of intersection of these three lines. A familiar definition, perpendicular bisector. A perpendicular bisector is a line that is perpendicular to a segment and intersects the midpoint of that segment. Section 5.3, to identify and use properties of triangles. First, concurrent lines. Concurrent lines is when I have three or more lines that intersect at one point. In the diagram, I have line K, line M, and line N. These three lines intersect at this common point. That common point is called the point of concurrency. In other words, it is the point of intersection of these three lines. A familiar definition, perpendicular bisector. A perpendicular bisector is a line that is perpendicular to a segment and intersects the midpoint of that segment. What we want to do here is double-click on that line. Notice I have two things that appear. I have this round circle, which when I hover over that with my mouse, I can then either rotate this segment or I can hit the drop-down menu and I can either delete it, but in this case, what I want to do is order it. And I want to send this to the back of this screen. Therefore, it brings the ruler to the front. Now I can see where this is actually lining up on my ruler a lot better. So I want to move this to 2.9. Then I want to bring in my protractor. And I want my black line in the protractor to be parallel to the base and then sit on top of the base. And the circle will be at the intersection point or the midpoint. Then I want to verify that this segment creates a 90-degree angle with the base. And since it does, this is a perpendicular bisector of the base. Let's just do one more. I'm going to double-click on my ruler. I'm going to rotate it so it is parallel to this side. Get as close as you can. And I see that the length of that segment is approximately 4.8. Therefore, I know that the midpoint must be at 2.4. So I'm going to double-click on the next segment to the right. I'm going to rotate that. So it looks somewhat perpendicular to that side. And then move it to approximately 2.4, which would be the midpoint of that segment. Now, I want to rotate my protractor. So I'll double-click on the protractor, rotate it. So it's going to be parallel to that segment. And have the intersection point at 2.4. That's not 90 degrees. So what I'm going to do is rotate that segment until it's 90 degrees. Now you can see that that is a 90-degree segment, but I believe I moved it off my 2.4. So I'll bring my ruler back over. I know as long as I don't rotate that segment again, it's at 90 degrees. Then I just drag that to 2.4. And as you can see, now that that is a 90-degree segment, it intersects at the midpoint, therefore that is a perpendicular bisector. from a previous slide, we've defined the point of concurrency is when three or more lines intersect at one point. It just so happens when I have three different triangles, being acute, right, and obtuse, our perpendicular bisectors intersect at a point of concurrency. We call that point of concurrency the circumcenter. And in an acute triangle, the circumcenter will always occur in the interior of the triangle. In a right triangle, the circumcenter will always occur at the midpoint of the hypotenuse. And in an obtuse triangle, the circumcenter will occur in the exterior of the triangle. Our next definition is a median. A median is a segment from the vertex of a triangle that intersects the midpoint of the opposite side. Given this acute triangle, let's find two medians. Let's start with one of the easiest ones. Let's find the midpoint of the base and create a segment from the vertex to the midpoint of that base. Here, when I slide my ruler along the edge, I'm going to get approximately the length to be 3.6. Therefore, my midpoint is at 1.8. And when I move my segment over, I realize that my line is on top of the triangle. Let's double click on my segment. I get my drop down arrow. Let's order that and send it to the back. Now that gives me a better view of where my triangle and segment are going to be. I want to move that to approximately 1.8. And when I do, I have a segment from the vertex to the midpoint of the opposite side. And that is a median. Let's find a median of another segment. Let's double click on my ruler and rotate that so it's parallel to one of the sides. And when I move this along the side, it's a rudimentary program, so I need to get it as close as I can. It won't be exact. And when I rotate it, I can see I'm going to get approximately 6.4. Therefore, my midpoint is at 3.2. I'm going to double click on this segment and remember to put it in the back. So I'm going to order it and send to the back. It already is. Then I'm going to rotate it so it can go through the vertex and intersects the midpoint of its opposite side. The midpoint is going to be at 3.2, since the segment is at a length of 6.4. So I just keep rotating and playing till I get it to go through the vertex and rotating through 3.2, or as close as I can get. And I think I have to rotate it back just one more bit. That's about as close as I can get to it. And now I have two medians of this triangle. On this slide, we have demonstrated three triangles. We have an acute triangle with three medians, a right triangle with three medians, and an obtuse triangle with three medians being created. And we already know that we have a point of concurrency when I have three medians in my triangle. That point of concurrency is called the centroid. In an acute triangle, the centroid is always in the interior of the triangle. In a right triangle, the centroid is always in the interior of the triangle. And in an obtuse triangle, the centroid is always in the interior of the triangle. Therefore, the centroid, by its definition, is always inside each of my three types of triangles. The altitude of a triangle is a segment from a vertex of a triangle that is perpendicular to the opposite side. Let's create two altitudes of this obtuse triangle. Notice on this slide I'm given segments, and also I have dotted lines. And I'm going to show you what we do with these dotted lines. Let's find an altitude to the longest side from the vertex opposite. So let's double click on the protractor and let's move that to the longest side. And what I want to do now is I can determine a perpendicular segment from this intersection point in the circle and have the segment go through the 90-degree mark on my protractor. All I need now to do is to move a segment, rotate it, so it's somewhat similar to this line measurement that I'm going to create through the intersection point and the 90-degree angle, but it has to go through the vertex. And let's also order it. So let's double click on that and order it, send it to the back, and then let's move this over and see how close I can get. I think when I put it through the intersection point, I do have a 90-degree angle, so I don't need to rotate it anymore. All I need to do is to move it so it is going through the vertex. Therefore, this segment goes through the vertex of the triangle and is perpendicular to the opposite side. Therefore, that is an altitude. That's very similar to what we've done on a perpendicular bisector and also on our median. But the difference is, in this triangle, I go back to my pointer to double-click on my protractor and rotate it. The difference here is that I'm going to have to create a segment that is from either of these two vertices and has to be perpendicular to the opposite side. So what I have to do is create a segment from this vertex and have it be perpendicular to this segment opposite that vertex. But any segment that goes inside the triangle will not be perpendicular from this vertice. So what I need to do is to extend this segment outside of the triangle. So I'm going to double click on this dotted line, rotate it horizontally, and I'm going to order that, send it to the back, and have that extend this line. Now I can just bring my protractor over, make sure that the line on the protractor and the dotted line are on top of each other, and then create a segment that is perpendicular to that dotted line, or the extension of that segment. Let's double click on the segment and order this one, and make sure that it's 90 degrees. And I have it going through the 90-degree mark, so I can move the protractor. And now all I need to do is make sure that it goes through the vertex. So that is my second altitude. Notice I have another dotted line. That dotted line is used to create an altitude from this vertex to this side. And to do that, I would double click on that segment and rotate it so it would extend through that segment. Let's order this. Now I would create a segment, and I'm just going to draw this in by hand, from this vertex that is perpendicular to that side. And as in the previous definitions, I have points of concurrency. And the point of concurrency of altitudes is called an orthocenter. The orthocenters intersect in an acute triangle inside the triangle. At a right triangle, they intersect at the vertice of the right angle. So here is where my right angle would occur. And notice the orthocenter is at that vertice. In an obtuse triangle, it would intersect outside the triangle. As you can see in my previous slide, if I extend this segment and all of these segments, they would extend to a point of concurrency outside my obtuse triangle. An angle bisector. An angle bisector is a line that divides an angle into two congruent angles. Let's create angle bisectors for this triangle. Let's start with the obtuse angle. Let's drag our protractor to the obtuse vertice and determine its angle measure. Make sure that the intersection point is at the vertex, and then determine the angle measure. Here, I have the line parallel or on top of my segment, and when I measure the angle, I'm going to get approximately 116 degrees. Now I'm going to make sure that this is double-clicked and order that, send it to the back. It already is. Now I'm going to rotate that segment so it goes through the vertex and also goes through the mark on the protractor at 58 degrees, which is the angle bisector of this angle, since the angle is 116. So I need to rotate a little more, get as close as I can. And that's about as close as I can get. Notice it goes through the vertex and also creates two congruent angles. To do another angle, I can do an easy one, which would be to slide it over this vertice. A more difficult one would be rotate the protractor until that intersects at the vertice, and the line matches up with the segment. Determine the measure of that angle. And here, I'm going to get approximately 36 degrees. And I need to rotate my segment, and I'll order it also. And at 36 degrees, this has to be approximately an angle at 18 degrees, but also intersects at the vertex. And that's pretty close. That could be as close as I get. Now I've created two angle bisectors inside that triangle. The point of concurrency of the angle bisectors of a triangle is called the incenter. In an acute triangle, the incenter occurs in the interior of the triangle. In a right triangle, the incenter occurs in the interior of the right triangle. And in an obtuse triangle, the incenter occurs in the interior of the triangle. Your assignment tonight will be to create altitudes, medians, angle bisectors, and perpendicular bisectors. Then what you will do is save that file and submit that file to me for grading.